Let's take some interesting problems on minterms and maxterms. So there are four chairs in a row. Let's say the chairs are A, B, C, and D. They are placed in a row. So B is beside A, C is beside B, D is beside C. So each chair may be occupied and it can be empty as well. So if a chair is occupied, then you say it is a 1, and if a chair is empty, you say it is a 0. For example, if A is occupied, I say 1. If B is empty, I say it's 0. If C is empty, it is 0. And if D is occupied, then it is 1. Okay, so assuming that this is the specification, that is A, B, C, D are four chairs in a row, give the minterm and the maxterm expansion for each of the following. So the first scenario is output F is asserted. It is a function of A, B, C, and D, and it is asserted if there are no adjacent empty chairs. Okay, to solve this problem, we need to write down the truth table. That's the most easiest way. So we have four chairs A, B, C, D. Since you have four chairs, they can have 16 combinations. That is, a chair can be occupied or not. Therefore, the first combination would be all four are empty. A, B, C are empty, D is occupied. A, B are empty, C is occupied, D is empty. So on. I can just write down the combinations. So that's 8 combinations. Let's keep moving. Let's keep going forward. So we have 16 combinations in total. Okay. Now the problem specification says that F is 1. So let's have F here. Let's keep this all the way down. So it says F is asserted if there are no adjacent empty chairs. So let's see for which combinations will F be asserted. In the first combination, here, you have A and B which are adjacent and they are empty. Therefore, F is 0. In the second combination, again A and B are adjacent and they are empty. Therefore, it is 0. In the third combination, again, it's 0. In the fourth combination, again A and B are adjacent which are empty. In the fifth combination, A and B are adjacent but one of them is occupied. That's fine. Then you have B and C. These are adjacent but one of them is occupied. That's fine. However, in C and D, both are adjacent but they are empty. Therefore, it's a 0. Now for this combination, one of them is occupied, one of them is occupied, and one of them is occupied. Therefore, F is 1. Same goes for this. One of them is occupied, one of them is occupied, and one of them is occupied. Therefore, it's a 1. Satisfies for the next combination as well, but here it fails. Therefore, it's a 0. Here it fails, a 0. Here it passes. Here it passes. Here it fails because it's a 0. And for the rest of the combinations, it's going to be 1. So how can you write F in minterms? Now you know that this is minterm 0, minterm 1, minterm 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Therefore, f of ABCD equals summation minterms, which are 5, 6, 7, 10, 11, 13, 14, and 15. So that's the first part of the problem. For the second part of the problem, you have a function g of ABCD, which is asserted if chairs on both ends are empty. Basically, the question says that since you have 4 chairs here, A, B, C, D, G is asserted if the chairs on both the ends, that is A and D, are empty. So look at all combinations where A and D are zeros, and your G will be 1 for that combination. So G would be here this one, then you have this one, that is M6. So 0, M0, M2, M4, M6, and that's about it. And for the other combinations, it's going to be 0. So that's G, and you can write the minterms as minterms 0, 2, 4, 6. Let's take part 3. So you have function h of ABCD, which is asserted if at least 3 chairs are occupied. Which means that 3 out of the 4 chairs A, B, C, D should be 1. Again, look for combinations where you have 3 ones. So your H would be 3 ones would first occur at M7, followed by M11, M13, M14, and M15. For the other combinations, you're going to have less than 3 number of ones. So that's the solution for this problem. So that would be summation M 7, 11, 13, 14, 15. Let's take the final part, which is you have a function j of ABCD, which is asserted if there are more people sitting on the left 2 chairs than on the right 2 chairs. So if there are more occupants on chairs A and B than in chairs C and D. Again, it's a simple problem. So J would be, it's going to fail in the first case because there are equal number of empty chairs on both A, B, and C, D. So there's no one basically. It's going to fail in the second case as well because in CD there is one person occupying, there is one occupied chair, but in AB there are 0 occupied chairs. So that would be a 0. Same thing with M2. With M3 you have 2 chairs that are occupied on the right hand side, but no chairs are occupied on the left hand side. Therefore that's a 0 as well. In M4 you have one chair that is occupied on the left hand side and no chairs are occupied on the right hand side. Therefore J is asserted. Now look for all combinations. M5 will be a 0 because there are equal number of chairs occupied on the left hand side and the right hand side. Same thing with M6. M7 would be a 0 again because 2 are occupied on the right hand side but only 1 is occupied. Now M8 would be a 1, M9 again is a 0, M10 is a 0, M11 is a 0. In M12 you have 2 chairs occupied on the left hand side, but on the right hand side you have 0 occupied, therefore it's a 1. Same thing with M13 and the same thing with M14. M15 is a 0 because 2 chairs are occupied here and 2 chairs are occupied here. So that's the solution for this problem. Now the problem can be complicated a little bit. What if there are 4 chairs A, B, C and D, but they are not in a row anymore, they are in a circle. So the neighbors of A are D and B, the neighbors of B are A and C, the neighbors of C are B and D, and the neighbors of D are A and C. So how would you do all these problems for, or how would you compute F, G, H and J for this particular problem here? So the problem, again, it's pretty simple. H, G, H and J will be the same. But F is going to change because earlier A and D had no connection, but now A and D are connected. Okay. Now if you look at F, it says F is asserted if there are no adjacent empty chairs. In this case, your F for M6 would be a 0 because even though A and B, even though one of these two are occupied, one of these two are occupied, one of these two are occupied, there is also a connection between A and D. But here they are not occupied. Therefore, your F would be a 0. So the only change would be M6 is no longer in F for the circular problem.